Okay.
All right, so welcome everyone to the Lockheed Martin Maryland Robotics Center seminar. I would like to acknowledge Lockheed Martin's continued support of our seminar series. This wouldn't be possible without their support. We have an exciting talk today. We have Professor Matt Schwager from Stanford University who will be talking about his research. He's been at Stanford for, I think, 3 years now.
5 years.
He was, 5 years, okay.
Yeah.
Well, time flies.
Yeah.
He was at Boston University for 3 years before that.
That's right.
And then a postdoc at Penn, and he did his PhD at MIT. He works on all things distributed control, distributed perception, distributed learning, and then as he was talking about earlier, he's going to be speaking about his recent work on distributed optimization. He has won numerous awards throughout his career, the NSF Career Award, the DARPA Young Faculty Award, numerous Best Paper Awards. On a personal note, I have followed Mac's work for a long time now, and Max is one of those names that I look forward to when I go through the conference proceedings, planning my which talks I want to go to and which posters I want to attend. Unfortunately, that's not going to be happening in an in-person format for a while, but I'm happy that Mac is here to talk about his recent work and share his thoughts on distributed control and optimization and game theory. So Mac, please take it away.
All right.
Just as a matter of note, as a protocol, if you have questions during the talk, just type it out in the chat box, and then I'll read out to Mac at various points during the talk. And then towards the end, we can have a more open Q&A where you can raise your hands and I can unmute you if you want to go ahead and ask your questions. So Mac, please take us away.
Thanks, Pratap, especially for that very kind introduction. I should say I always look for your name as well when we go to ICRA and IRO, so it's like a mark of quality. I know that you're going to be having good papers and good talks. Okay, so, and I should say thank you also for inviting me for this seminar. It's really a pleasure. I wish I could be there in person. I don't think I've ever been to University of Maryland, actually, so I would have loved to have come in person, but we'll save that for a future date. Okay, so today I'm going to talk about multiple robots, always, and specifically enabling multiple robots to cooperate using tools from distributed optimization. And then there's a certain symmetry here, also enabling robots to compete with one another and also with humans or human-driven, say, vehicles, using ideas from game theory. So there's a strong parallel between distributed optimization and game theory. I see these as kind of two sides of the same coin with sort of different assumptions. So I'm hoping to highlight that throughout the talk. So maybe I'll start with just introducing you all to some of the work that I do and the kinds of problems I'm interested in. So I run the Multi-Robot Systems Lab at Stanford, and we work quite a bit with drones. We're in the Aero-Astro department, so we're interested in things that fly. And so a lot of our work has to do with low-level nonlinear feedback controllers and also higher-level trajectory optimization and planning for drones. But our bread and butter is really designing algorithms for cooperating groups of drones that cooperate, or groups of robots in general that cooperate. So here in the video, I'm showing an algorithm that uses ideas from virtual structures to allow a swarm of drones to coordinate their actions and also to allow a single human operator to efficiently control that swarm of drones through a simple joystick. So here the drones, for example, take charge of their own collision avoidance and trying to maintain the formation, and the human just takes charge of the high-level control action. I'm also really interested in cooperative perception. So here's an example where drones have downward-facing cameras, and they're using shared image features between neighboring drones' cameras to figure out their relative pose and then to use that as a feedback signal to fly in a desired formation. I'm interested in quite a bit beyond just drones. So here's a very small fixed-wing aircraft that we've developed an autonomous controller for. And beyond aircraft, I'm interested in autonomous driving, very much recently in autonomous driving, and also in autonomous ground vehicles of various sorts. So I'm also interested in adversarial situations or game theoretic problems. So here you have an example where there's a pursuit evasion problem with a ground robot trying to run away from and hide from these aerial drones that are trying to pursue and keep track of the ground robot. And I'm also very much interested in robots in the wild. So all the algorithms that I study, I try to produce as much as possible realistic deployments for these robots. So here's an example of a deployment we did in a forest, a research forest in Massachusetts, where we deployed a group of 5 drones to autonomously monitor the forest. So they basically had downward facing cameras. They flew out and over the forest so that each drone took images of a different part of the forest. And the idea was that this would help people managing the forest to assess the overall health of the forest. So that's high level the kinds of problems I'm interested in, the kinds of things I've done in the past. So you might ask, why multi-robot systems? Maybe I'm preaching to the choir here. I know Pratap works primarily in multi-robot systems, and probably many of you are interested in this topic as well. But I'll just sort of review the basic motivation. So oftentimes multiple robots can perform tasks more efficiently, more cheaply, more robustly than a single robot. So you can imagine any task that's sort of large scale and distributed has this property, right? So using groups of robots to clean up oil spills or chemical spills, or generally to map sort of hazardous chemicals, this can be done much more efficiently with multiple robots than a single robot. Precision agriculture, you have crops spreading over many thousands of acres, and those crops can be tended more efficiently by a group of robots rather than just one. Forest firefighting, same idea. You can imagine a group of drones or a group of fixed wing aircraft going and monitoring the evolution of a forest fire as the front of the fire moves through the forest. So this is actually really timely right now in California. We're having just a tragic and historically bad fire season. Over 4 million acres have been burned so far. And we're actively working in the lab on algorithms for both monitoring and tracking forest fires, and also fighting forest fires with groups of robots. So disaster relief, same thing. Multiple robots can more efficiently identify survivors and identify and map rubble fields than a single robot. You can imagine problems in construction, distributed construction, for example, on-orbit construction, if you want multiple space robots to construct a space station, or on the Earth, if you want multiple robots to construct a structure, a building, or do manufacturing. You can do these tasks in parallel, right? So oftentimes manufacturing consists of multiple parallel tasks that need to be synchronized and then synced up together to ultimately produce the final result. So this is a problem in multi-robot systems. And I'd say the killer app recently in my lab has been transportation systems, autonomous vehicles. So traditionally, autonomous vehicles have been studied as a single robot, right? You have one robot bristling with sensors, and you want that robot to navigate the roads and not hit other robots. And our argument is that indeed, actually, autonomous driving is a problem in multi-robot interactions. Human drivers drive cars while they're very much aware of what the other cars around them are doing and predicting what they will do in reaction to what I do, and so on. And so we'll be talking quite a bit about autonomous driving in this talk. Okay, so let me dive into the specifics of this talk. So distributed optimization is going to be the first half of the talk, and then game theoretic planning is the second half of the talk. You'll see lots of similarities in the underlying tools for these two problems. The main difference is in the assumptions about what the robots are trying to accomplish and what they know about one another. So in distributed optimization, the robots are working together. They have one common objective that they're trying to optimize. And in competition, every robot is working independently and has its own objective that it's trying to optimize. Otherwise, it's more or less the same thing. There's lots of things trying to optimize their own objective functions or their own piece of the same objective function. So let's start with distributed optimization for collaborating robots. So I've been really interested in distributed optimization as kind of a general purpose tool for multi-robot planning and multi-robot perception. So I'm going to talk about lots of different applications of distributed optimization to various domains within multi-robot systems. So one of those domains is distributed target tracking. So suppose you have an autonomous vehicle fleet. These are the cars in green. And suppose these vehicles have a vehicle-to-vehicle network. So currently, autonomous cars typically don't have a vehicle-to-vehicle network, but one could very easily imagine a future in which they will have to by mandate of some regulations, right? So our question is, what can we do if we have a vehicle-to-vehicle network? Well, clearly, what we would want to do is use the multiple sensors and multiple sensing perspectives of all the different vehicles to better track and better predict the trajectories of other cars or pedestrians or bicyclists or whatever other moving things in the environment. So that's what's going on in this figure, right? The green cars are an autonomous vehicle fleet, and they're working together to cooperatively estimate the trajectories of the red and the blue car. Maybe those are human-driven cars. Another example is distributed manipulation. So I'll be talking about this in some detail as well. Suppose you have a group of, maybe they're manufacturing robots, maybe they're domestic helper robots. And these robots are mobile manipulators. So they have manipulators and a mobile base, and they latch on to something they want to move. This thing they want to move is a rigid body, and they want to work together to maneuver this rigid body through the environment along some desired trajectory or towards some desired goal. And furthermore, each robot has its own local sensing. So one robot may sense an obstacle that no other robot senses. So how do these robots coordinate to find a common trajectory plan for the obstacle, for the object, while avoiding collisions with all of the obstacles that they locally sense? So I'll dive into these in detail, but first I want to step back and say something about distributed optimization. So, and in the abstract, what is distributed optimization? So it is what it sounds like. You have an objective function, and you would like to minimize that objective function through a distributed algorithm. So it's a large research universe, and most of the research in this universe is geared toward parallel computing. You can imagine why, right? Typically in problems involving machine learning or in general optimization problems, we are interested in distributed solutions for the sake of speed through parallel computing if we have multiple parallel cores. But the assumptions that underlie parallel computing are very different than the assumptions that underlie a network of robots. So what I'm talking about is specifically a flavor of distributed optimization that is suited to be distributed over a graph that's kind of a mesh network that evolves over time as the robots change their communication topology, right? And so what that means is that the algorithms I'm interested in are of the following nature. Every robot, I'm associating robots with nodes in the graph and communication links with edges in the graph. Every robot has its own sort of computational thread in the optimization. And these threads compute through iterations ultimately the globally optimal solution of a joint objective value. And we require that these threads of computation only need information from their local neighbors. So that's what I mean by distributed optimization, is iterations that only require local communication over a graph. And of course, this is associated with a multi-robot network. And so in distributed optimization, the standard form that is treated for a candidate for being distributed is what's called separable. So you have one global objective, call it capital J, and we have to be able to represent that as a sum of local objectives, which I'm showing here is sum over I of Ji. And so now Ji is an objective that is owned, quote unquote, owned by robot I, and Xi is a state variable that is a set of state variables that is owned by robot I. And at the end of the day, we want all the robots to coordinate to optimize this joint objective, which is the sum over I. So that's the setup we're looking at. So within this narrow idea of distributed optimization over a graph, there's still quite a bit of work. So this goes back to the work in the mid-'80s of Tsitsiklis and Birtsikas. It goes back to John Tsitsiklis's PhD thesis, actually, and then a textbook that Tsitsiklis and Birtsikas wrote afterwards called Distributed and Parallel Computing. And the main algorithm that they proposed is called consensus gradient descent, or distributed gradient descent. And this algorithm, I would say, kind of went dormant for some time and then regained a huge bump in popularity through the movement of consensus algorithms in the control theory community. And one of the main champions of this work was Angelia Nedic, and she's still very much active in distributed gradient optimization methods. And she's produced some of the seminal works, most recent seminal works in this area. So high level, what this whole framework of optimization does is every robot I, every agent I computes a gradient of their own component, Ji, and then produces a sort of consensus averaging term with the local neighbors, and then takes a gradient step, which is a combination of these two things, the local gradient and then the local consensus. So I'm not going to be talking about this work in this talk. This is just purely to tell you about what is out there in the research community. But I will tell you that this is by far the most productive framework for distributed optimization on graphs. There's an enormous literature here. This is not what I'm doing. And in fact, what I'm proposing here in our own empirical studies performs much better than all of the work that we're aware of in gradient optimization. So the work I'm considering here relies on an algorithm framework called consensus ADMM. So ADMM is its own sort of meta framework for optimization. It stands for Alternating Direction Method of Multipliers. It was originally proposed way back in the 70s. And it's just a general technique for dividing an optimization problem into different blocks and then being able to distribute the optimization through blocks. It is designed specifically for the parallel computing paradigm. It does not obviously lend itself towards the graph-based optimization paradigm, except for the recent work in 2010 that I have cited here, Mateus et al. They took this ADMM framework and very cleverly recast it in a way that can be optimized over a graph. And so this is called consensus ADMM. It's what I call consensus ADMM. Actually, Mateus et al. Did not call it that, but they were the first to propose this algorithm. Since then, there have been lots of various papers that have used consensus ADMM like algorithms for various problems. And then there are lots of other methods, some that depend on augmented Lagrangians and various other forms of methods, and I won't talk about those. So I'm specifically talking about consensus ADMM here, and specifically an algorithm that we have developed in my lab called SOVA, which is actually a generalization of consensus ADMM. So let me first talk about consensus ADMM, and then I'll talk about SOVA. So consensus ADMM, again, I have the more complete reference down there. It's a very beautiful and elegant algorithm. Looks like this. So you have your separable optimization problem shown here. So every robot is in charge of its own component of the objective, J sub I. And we decouple these optimization problems saying that every robot has its own copy of the optimization variables xi. And then we later impose consensus on these optimization variables through a constraint. So xi has to equal xj for all edges in the graph. So you can see why it's distributed over the graph, right? These constraints are distributed over the graph. So what this means in practice is that you might have one global optimization variable. Maybe it has dimension p, maybe it lives in RP, right? Now, in order to distribute the problem, each agent makes a complete copy of that optimization variable, also a dimension p. So we've transformed a p-dimensional problem into an n times p-dimensional problem. We've made it a much bigger problem, but for the benefit of being able to derive a distributed algorithm for solving the problem. And essentially, the way we get this distributed algorithm is we take these decoupled problems that are coupled through a constraint. We turn the crank of ADMM. I'm not going to go into the details of the crank of ADMM, but in the end, ADMM leads you to distributed iterations for optimization. So every node in the graph computes these iterations, and at every step k, each iteration only depends on the results from your neighboring nodes from the previous time step. And the iterations follow a very common template, which always emerges from ADMM, which is there's a primal step, which involves solving your own local optimization problem. That's this guy. So within one time step k, you're solving a smaller instance of your optimization problem locally. And I'll talk more about what that looks like. And then there's what's called a dual update. So the p variables are dual variables, they're Lagrange multipliers, that in the end of the day, after all of your iterations are done, they enforce this consensus constraint. So we find that in practice, this works way more robustly, way faster than distributed gradient descent. So this is consensus ADMM. It has the obvious drawback that you're solving an instance of the problem that is much bigger than it needs to be. You've just copied the decision variables wholesale on each robot. So what we've proposed recently in an ACC paper, the reference is there at the bottom, is what we're calling separable optimization variable ADMM. It's a generalization of consensus ADMM. So this, the acronym is SOVA. And this is work by my two students, Ola and Trevor. Their pictures are shown up there. So what's the idea? It's kind of a simple tweak, a simple change to the separation of the objective function. So instead of ensuring global consensus between the complete state of xi and the complete state of xj, we just ensure consensus on a few elements of xi and xj. And so we call this a separable optimization variable. And so it is the case that some problems, the problems I'll be talking about later in this talk, have this property that that the optimization variable can be naturally decomposed among the agents. There's no need for every agent to have a complete copy of the optimization variables. And one example you can see immediately is in distributed target tracking. So this example I talked about at the beginning with a fleet of autonomous cars tracking a target. So I'm an autonomous car and I only see the target for a short time window. That's all I care about. I only have measurements over that short time window. That's all I care about. So my fragment of the optimization variables would just pertain to that time window. And then my other neighbor has a different time window and his fragment would pertain to that time window. And then we require consistency constraints so that the overlaps in these windows have to be equal. So in this case, for example, the last element of x1 has to be equal to the first element of x2. And so A12 is just a selector matrix that pulls out the last element of x1. And then A21 is the symmetric selector matrix that pulls out the first element of x2. Now, in general, these don't have to be symmetric. You can see the details in our paper. It could be that, you know, the thing that x1 needs to be in consensus with for x2 may be different than what x2 needs to be in consensus with for x1. And furthermore, they don't have to be selector matrices. They can be just any matrices. There's no requirement specifically on what these matrices have to be. So they can be various linear combinations of the state variables. And at the end of the day, you do the same procedure. You turn the crank of ADMM and you get iterations. And the iterations have the same form. You have a primal update. So again, node I, robot I, computes its own local primal update, which only requires its own information, and it only requires communicating the results of the local updates from your neighbors at the previous time step. And so again, this is an optimization in and of itself. And it's an optimization of what's called the Augmented Lagrangian. So you're probably all familiar with the Lagrangian. The Lagrangian is for constrained problems. So in the Lagrangian, you have your objective function. In this case, it's a local Lagrangian. It's just the objective for robot I. And then your own constraints. So this is a Lagrange multiplier, and this is the decision variable for robot I. So this is the regular Lagrangian. My pointer's disappearing. There we go. This is the regular Lagrangian. An augmented Lagrangian is the regular Lagrangian plus a quadratic penalty term. And that's what you see here, the quadratic penalty term. So I want to be clear, augmented Lagrangian methods are very common in optimization, and it's not a soft penalty. There's no approximation here. So if you solve for the global optimum of your augmented Lagrangian, you have solved your constrained optimization problem. And the typical method for augmented Lagrangians is a dual ascent technique. So you're trying to essentially solve a minimax problem, just like you do with the Lagrangian duality kind of approach. And so you minimize with respect to your primal variables, and then you do a gradient update step to a gradient ascent step with respect to your dual variables. And that's what's happening here. So I'm going to talk. So, right, so that's the dual update step that you see here. Right, so what I'm trying to communicate here is that the augmented Lagrangian piece, the extra quadratic penalty, there's no approximation here. This actually gives you a hard satisfaction of the constraints. So this primal problem can be computationally limiting if it's a difficult primal problem to solve. However, in some cases, it can be solved in closed form. And then the primal update is actually a closed form algebraic update rule. And then this whole optimization scheme can be done in closed form with algebraic updates. And the special case that's of interest where this is true is when your objective function is actually an unconstrained least squares problem. Then J is unconstrained least squares, and then you have a linear term and a quadratic term, and you can combine these to make a new unconstrained least squares problem, and then you can solve everything in closed form. So that's the common thing that's treated in the literature, is when this can be solved in closed form. And so we're comparing now our SOVA method, where we've decomposed the state into these little fragments on each robot, versus consensus ADMM, where every robot has a complete copy of the state. And it's not surprising that ours converges much faster. So it depends on the topology of the graph, right? Because the topology of the graph tells you how big your small optimization problems are, your local optimization problems are. But for a fully connected graph, we converge something like 2 orders of magnitude faster than consensus ADMM. For a chain graph, the advantage is much more clear because we have fewer neighbors, and so we converge considerably faster, 3 orders of magnitude faster, something like that. And it's very much dependent on the specifics of the problem, the graph topology, the number of agents, and so on. One thing that's clear is that if your graph topology is such that that adding agents keeps the same connectivity, so the Fiedler value, which quantifies the connectivity of the graph, if that's constant as you add agents, then our SOVA algorithm is constant time in the number of agents. So you can solve successively bigger and bigger optimization problems with more and more agents without any sacrifice in computation time. This is very much different from consensus ADMM, where this computation time increases exponentially. So this is a log axis as the problem instance increases. Okay, so how am I doing on time? Okay, so now I'm going to talk about how we use this tool, this SOVA distributed optimization tool, to solve multi-robot tracking with multiple dynamic targets. This is the problem I introduced before. And then I'm going to talk about how to use this to solve distributed manipulation. So what I will be talking about is joint work by Ola and Trevor, who were also involved in the SOVA work I described before, as well as Javier and Alex. These are all folks in my lab. And this was presented just recently at the ICRA 2020 over the summer. And we're very pleased and honored to have won the Best Paper Award in Multi-Robot Systems for this work. So we have the green cars. Each one has its own sensor, and they're working together through distributed optimization to track the trajectory of the red car. So we assume that we have a motion model for the target that's driven by Gaussian white noise. I'm going to assume this is linear for now, a linear motion model, but it doesn't have to be actually. We have more recent versions where this is nonlinear motion model. And then each robot has its onboard local sensors. So each robot has its own sensor model. I'm again going to assume that this is linear for the sake of simplicity, but it doesn't have to be. And we have Gaussian sensor noise. So you can see that what I'm talking about here has the flavor of a Kalman filter. I'm talking about something that would be solved with a Kalman filter if everything's linear, or an EKF or something of that flavor if it were nonlinear. And at the end of the day, we're trying to find the Kalman filter result, which is the posterior distribution of the target over all of the measurements over all the robots. So the globally optimal solution would be to take all measurements from all robots, pool them in one computer, and then compute the Kalman filter. But that's very inefficient, right? The robots have LiDARs with like huge, megabits of information every time step. We don't want to share all this. It'd be very bad use of bandwidth over the network. So we want to solve this problem in a distributed way. And in particular, I'm solving what's called the maximum a posteriori problem. So the posterior is the result from the Kalman filter. That's P of X given all the measurements over all the robots. And I'm going to say that my trajectory estimate is the maximum of this. So it's the most likely given this posterior distribution. Okay, so I'm solving a Kalman filter-like problem, but purely through optimization. There's no Kalman filter anywhere in this algorithm. So it's a new way of thinking about Kalman filtering. So here's the optimization problems. Find the maximum a posteriori of this posterior distribution. And we do what's common for these kinds of sensing problems. We take the posterior, we take the negative log of the posterior, and this turns into a least squares kind of problem. So that squared term was in the exponent of a Gaussian and now it turns out to be just a least squares problem because I've taken the negative log. And this negative log turns out to be separable. It's not too surprising, right? But you have a sum over each robot of component objectives, and I'm showing you here one component for robot I. And this consists of 3 terms: a motion prediction error term. So this says what my motion model says the robot does versus what I see it do. The sensor measurement, which is the difference between what I expect to see versus what I actually see for my sensors. And then there's a prior term, which I'll talk about, but the prior term is required to make this a recursive filter. So the nature of this algorithm is that we solve an optimization problem within each time step. And then we use the prior to loop this to the next optimization problem and then solve that within one time step and then loop to the next optimization problem. So at the end of the day, this becomes our per robot objective function. We do the SOVA, or the consensus ADMM decomposition, and find per agent iteration rules that look like this. So you have the primal update here, which is a optimization problem, and then the dual ascent step here. And the primal here is, this is now an unconstrained least squares problem. So you can solve this in closed form. It becomes a closed form algebraic update. And you might ask, okay, cool. So what does this look like in one frozen time instance? What does the evolution of this optimization algorithm look like in terms of the estimate of the trajectory of the target? So I'm showing you here, I'm going to play and stop, showing you here the evolution from the perspective of one robot. So you see this blue thing is one robot, and this is the trajectory estimated of the target estimated by that one robot over time as it solves iterations of its SOVA type filter, or SOVA type optimization. And then I'm going to show you the same thing over all the robots that are cooperating together. You can see now multiple curves that reach a consensus over time. So you can see this is at one frozen time step, the iterations of the optimizer agreeing upon a trajectory for the target. So you might ask, is there a benefit of cooperation? If one car were to just take its own measurements and estimate the target trajectory based on those measurements, how well does it do versus how well does our cooperative estimator do? So there's a huge benefit, as you can see here. So this is the average overall cars by using only their own measurements. And this is the average overall cars by using this cooperative estimation. It's something like 4 orders of magnitude better in terms of the mean squared error. So there's a huge benefit to cooperation. So now we want to ask, how well does this distributed optimization method perform with respect to a consensus Kalman filter? So in Kalman filtering, there are various flavors of distributed Kalman filtering. This goes back to an original work by Olfati Saber, who is one of the primary movers in the consensus movement in the controls community. So he developed something called the distributed Kalman filter. In our experience, this actually is not very effective, but there is a much more recent work called the consensus Kalman filter with some slight tweaks over the distributed Kalman filter that works much better. And so we've used this consensus Kalman filter from 2016 as our baseline to compare against. And the idea is that you just take the existing Kalman filter equations for each robot individually, and then you combine them with a sort of a consensus step among robots. So it has a flavor actually very similar to consensus gradient descent. And it's very different from our algorithm. Our algorithm has no Kalman filter in it, right? Okay, so consensus Kalman filter has the same flavor as our algorithm. You freeze time, you receive a measurement, you freeze time, you do iterations within your algorithm to find your estimate for the thing you're trying to track, and then you take the next measurement, and then you do little iterations, and then you take the next measurement and do little iterations. So the plot on the left is within one frozen time instance. These are the optimization iterations. And you can see consensus Kalman filter converges much more slowly than our filter. The acronym we chose is distributed rolling window tracker. There's some details in there that I haven't talked about with regard to rolling windows. Don't worry about it. So it's SOVA applied to this tracking problem. And you can see it's something like at least an order of magnitude lower error for the same number of communication transmissions among the robots. And then now, if we think of how this behaves as a filter over multiple time steps, this is what I'm comparing on the right plot. So we have consensus Kalman filter in the red and our distributed rolling window tracker in the blue, and then the fully centralized globally optimal tracker in black. So that's the centralized Kalman filter if all of the measurements were available in one computer. I think it speaks for itself, right? The blue line almost perfectly overlays the black line. It means our distributed rolling window tracker essentially reproduces the same performance as you would get from the centralized Kalman filter, whereas the consensus Kalman filter doesn't come close. So the choppy line is the minimum mean squared error. Excuse me, the choppy line is the minimum mean squared error of the mean estimate from the consensus Kalman filter, and the dotted line is the trace of the covariance matrix. And you can see the tracker does worse, and it's less confident. It's even less confident than it ought to be. If these things were consistent, this dotted line would hit across the mean of the choppy line. So it's both not performing very well, and it thinks it's performing even worse than it is, versus ours, which is quite consistent and very close to the globally optimum. Okay, so I didn't talk about how to make this a filter. I just talked about the optimization problem within one time step. So how do you make it a filter? What you do is you take the result from your previous optimization iterations, call that x hat, and then you use it within a prior term in your next round of iterations. So in your next round of iterations, you have two states that you're optimizing over, the current state and the previous state. And the previous state, you're trying to match it as close as possible to what your estimate was from the previous state. So this is the tie-in mechanism to make it recursive. And this P inverse is the information matrix, or the inverse of the covariance matrix, that only agent I found from the previous state. And I haven't talked about it, but this comes for free in the distributed optimization procedure. So you get this information matrix for free, even though you're not using a Kalman filter. And it turns out this is a little bit conservative over the truly centralized filter. And the conservativeness has to do with exactly the form of this information matrix. I don't want to get into details, but it's probably best illustrated from this picture here. So this is the trace of the information matrices local to every robot, summed up at each time step. And then the black line is the trace of the centralized information matrix. So if we were exactly reproducing the centralized filter, there would be no gap between the sum of the colored bands and the black line at the top. But you can see here, there are very tiny gaps. There's just a tiny bit of white space in a few of these places that you can see. And that's the suboptimality of our filter. So it's interesting here. So this is why in the previous plot, the black line didn't perfectly overlay with the blue line. There's a tiny bit of suboptimality here. And it's also interesting here that each color represents a different robot. So there's something else going on here that I haven't talked about in detail, which is there's a handoff procedure. So the set of robots that are tracking the target at this time instance are different from those tracking the target at this time instance, but yet there's summed information still has this consistency across time instances to reproduce the nearly centralized result. Okay, so let me show you how all this works together in a large-scale, high-fidelity simulation. So this is a simulation that we produced in the environment called Carla. Carla is a relatively new autonomous driving-oriented simulation environment. So what we did is we kind of built a mini city, which you can see here. And the mini city has 50 autonomous cars that are communicating over a vehicle-to-vehicle network, and 50 human-driven cars that are not part of the vehicle-to-vehicle network. And so the task here is to have the 50 autonomous cars continually track the 50 targets, the 50 non-autonomous cars. So here you see this kind of target handoff over time. So the green cars are the autonomous cars. You can see their network connections evolving over time with the dotted lines. And the red car is a target that's being tracked, and then the responsibility for tracking is being handed off from one car to the next. And here we're just comparing the consensus Kalman filter versus ours. You can see ours converges much faster. This shows you sort of in a real-time animation how much more quick ours is compared to the consensus Kalman filter. Okay, probably a good time to break. I'm going a bit slower than I expected, and that's totally fine. So why don't I break for questions? Is there anything I should address here?
Yeah, so there's a few questions from John.
Sure.
Let me try to summarize them. And John, at the end, when we open it up, you can ask more detailed questions. But for now, let me just summarize the questions. I think they all have to do with the topology of the graph, and specifically this optimization is, are you doing this over the communication graph or the collaboration graph? The fact that these two are not the same and have an impact on the performance of the algorithm. And then he makes a comment saying that in some of his work, they've shown that small world-like graphs and expander graphs can speed up 10-fold distributed algorithms running on the collaboration graph. So can you comment on that aspect of this?
It's an important distinction. Yeah, thanks. That's a very good point. And I fully agree that certain graph topologies either promote consensus or inhibit consensus. So there is a distinction here between the communication graph and the graph that arises in the distributedness of the optimization problem. And we have made an assumption here. So it's problem specific, exactly how well those two things match up is problem specific, right? So we have made an assumption in this distributed rolling window tracker that any two cars that see the target at the same time are within communication radius. It may not be true all the time, but there are ways you can relax that assumption. But that's essentially the assumption we've made. So that means that essentially the graph required for the distributed optimization is a subgraph of the communication graph. It's a great point.
Thanks. And John, I think when we open it up for Q&A at the end, you can ask follow-up questions. But there's one more question here, has to do with the Kalman filter work. Specifically, there's often delays in communications in networked systems, and that can have an important effect on the performance and convergence. Have you looked at incorporating delays in communication as well as actuation?
It's a great point. So we have looked at this empirically, but this is not reflected in our paper. We didn't present any results in the paper. I'm aware of some papers that look at consensus ADMM style distributed optimization algorithms and consider those under asynchronous updates, which would occur if there are communication delays. And the analysis is complicated, but the end message is the algorithm is very much delay tolerant. And this is what we found in practice as well. The algorithm is very much delay tolerant, meaning you won't have problems with convergence if there are time delays. There's always limits to this, right? You can always invent a time delay that will make convergence so slow that you don't converge by the time you receive your next measurement. But from a high level, it is robust.
Awesome, thanks.
Thanks. Okay, so in the interest of time, I'm gonna just really sketch this next piece. So it's probably not too hard to believe that we can use this distributed optimization framework that I've called SOVA to solve distributed manipulation of the following kind. You have mobile manipulators, they're rigidly grasping onto a rigid body, and they want to agree on a trajectory for that rigid body to manipulate the object through an environment. The environment has obstacles, those obstacles are only sensed by robots locally. So robot I sees one obstacle that is not seen by anybody else. So the naive thing we could do is share our sensor measurements for obstacles throughout all the robots and acquire a globally consistent map. It's very inefficient. So SOVA allows us to avoid doing that. Every robot only cares about its own obstacles, and then they seek to reach convergent consensus rather on the trajectory that they optimize for the object. And because you require that the robots reach consensus, and every robot requires that it avoids its own obstacles, you get the fact that there's no obstacle collisions, even though no one robot knows about all the obstacles. So I'm going to breeze through the details in the interest of time. At a high level, this becomes you set this up as a trajectory optimization problem, and it becomes separable among the robots. The constraints also turn out to be separable. I'm going to fly through here in the interest of time. What's interesting is that the constraints are separable in the sense that robot I only needs to enforce the constraints that it's aware of from its own local sensing. And then you ensure global consistency through this trick of SOVA, which is that the object trajectory that you solve for as robot I needs to be equal to the object trajectory that robot J solves for. So now this decomposes into n separate optimization problems, one for each robot, where robot 1 is trying to optimize its object trajectory and its own control input, so its own forces and torques. And then the coupling is just through equality on the object trajectory. So existing methods to do this have looked at robot 1 needs to keep a copy of all the forces and torques for all the robots. So it's not scalable, but ours is scalable. So this just shows that you can push through the iterations for SOVA. So you end up with a primal update where you solve a primal problem and then a dual update. What's interesting here is the primal update for the robot is itself a constrained optimization. So the primal problem itself involves collision avoidance and consistency for the rigid body dynamics of the object. So each instance now of this primal update requires solving its own constrained optimization problem, its own minimax problem, and we do this through its own dual ascent. So we optimize primal variables and then do dual ascent on the local multipliers to enforce collision avoidance, that's CI and DI, and so on. And so this all happens within one primal update of SOVA, and then we go to the dual update of SOVA to enforce the consistency constraints. And so this is all done in a receding horizon loop. It's fast enough to do it online in a receding horizon loop because our algorithm converges very quickly. By the way, this specific version of SOVA applied to distributed optimization, manipulation with constraints, we call it SOCM Loco. You need an acronym, right? You need a cute acronym. So this is our cute acronym. That stands for Separable Optimization Collaborative Manipulation with Local Collision Avoidance Constraints, SOCM Loco. So it's done in a receding horizon loop. Robot Eye starts with the trajectory it solved for at the previous time step, and then it takes its new sensor measurements and it shares iterations with its neighbors and then computes a new trajectory. It applies its computed force and torque for one time step, takes new measurements, and then does this in a loop. So it's similar in flavor to the filter for tracking, right? You're doing an optimization within each time step of the receding horizon. And this is how it performs at the end of the day. So you have the 4 robots and the rigid object that they're cooperatively maneuvering through this obstacle field, and only the robot that's closest to each obstacle knows of the existence of that obstacle. Okay, so I'm gonna just give you some teasers of some other things we're doing with this SOVA distributed optimization. So we're looking at problems that involve contact and grasping and regrasping. So in trajectory optimization, there's a certain flavor of problems that involve contact. They're called, planning through contact. And they involve a particularly challenging kind of constraint. It's a particular non-convex constraint. It's called the complementarity constraint that encodes the normal force, the reaction forces, and the friction forces due to contact. And so we've been able to formulate our SOVA optimization for distributing planning through contact. So I'm going to show you here on the left is an example where the 3 blue robots are grasping through contact this orange object and maneuvering it towards a goal. And then I'm going to show you an example on the right where the blue robots are playing soccer and the orange thing is a ball. It's an inanimate ball. And so the blue things can apply contact forces and kick the ball. And they're trying to get the ball and trap it ultimately into this goal position. So that was a bit fast, but you can see how that works. Completely done distributedly in a receding horizon loop. Every robot optimizes its own actions and uses this SOVA thing. Okay, we can also solve a variety of other problems. So one thing that another student is looking at is distributed postgraph optimization. So what is postgraph optimization? Well, it's SLAM. You've all heard of SLAM. It's the back end of SLAM. So in SLAM, you have a front end and a back end. The back end is really the heart of SLAM. It's how you take all of your measurements and all of your pose estimates and make them consistent across a whole map of poses. And so distributed multi-robot SLAM is a big problem, right? If you have, for example, a network of autonomous cars and they want to cooperatively build a SLAM map of a city at very large scale, you need to be able to efficiently scale up SLAM in a distributed way. And SOVA is a perfect candidate for doing this. So here the graph is as follows. Every robot at every time instance has a pose, and neighboring time instances are linked up with an edge for the same robot. And then 2 robots, when they have a mutual observation of one another's poses, there's a link there between robots. And so you have this huge thing, it's called a Postgraph, and it's partitioned among the robots. So one piece of the Postgraph belongs to robot I, one piece belongs to robot J. And here's what SOVA does with that partition Postgraph. So it looks like Humpty Dumpty being put back together again, right? Every robot has one eggshell piece, and the fragments realign through SOVA, and you produce the end result. So this data set is actually a synthetic data set, right? Obviously, you don't have a bunch of cars driving around on a sphere, but this is a standard benchmark for centralized SLAM. And so we're using it for distributed SLAM. So the pose graph is just every pose is sort of on the surface of this sphere. This is graphically appealing. Okay, so very much running out of time. I'm going to switch now to talk about game theoretic planning. So this was all distributed optimization. It was all unified by the fact that the robots were in communication and they were all working together to optimize a common objective, which was the sum of their individual objectives. What's different in game theory is that every robot has its own separate objective, and they're not trying to optimize a common objective, and usually they don't have communication to coordinate their actions. So what do we do? And why are we interested in this? So we're interested in this for a number of reasons, but one of the primary reasons is drone racing and car racing. I just think it's exciting to imagine autonomous drone racing and autonomous car racing. I think this is a really cool problem to motivate research. So here you have on the video, human piloted drones. This is actually a semi-pro drone league. It's called First Person Viewer FPV Drone League. And you can see that the drones are, right, so the drones have cameras on board, and the images from the cameras are streamed directly to some goggles, and then the pilots are flying based on the goggles. There's a lot of amazing stuff going on here, but the thing I want to draw your attention to is the racing strategy. So the pilots have to think about what the other drone pilots are doing, and they're jockeying for position. So if they're in the lead, they're trying to maintain their lead position, trying to defend their position. And if they're behind, they're trying to find an opportunity to pass. And so there's collaboration here. It's not just who gets around the path fastest, it's how to get around the track fastest while tricking or strategizing with respect to your opponents. And we have managed to produce a drone racing policy that does this. So it strategizes its plan in a receding horizon fashion to coordinate with the other drones on the track. And you can see this in the video here in the lower right, where the green drone was using our game theoretic planner. You just passed the blue drone, and all the perception is going on board. I'm not going to talk much about perception here. I'm going to talk about planning. So this is a fun and exciting problem, but it's also true that game theoretic planning is very important in autonomous driving, or in any situation where you have a ground robot that has to navigate among humans. This is inherently a game theoretic type situation. Every agent, whether it's a robot or a human, has its own objective, which is try to get to your goal as efficiently as possible. But they have to negotiate with the other agents. So maybe there's not overt competition. Maybe it's not a zero-sum game as it is in racing, but still, there's still competition all over the place in autonomous driving or in any situation where you have multiple robots with their own independent objectives. So, right, so how is a game separate or different from distributed optimization? So in a game, every robot has its own objectives. I'm going to call that J sub I here for robot I. And that objective is in general a function of not only the robot I's decision variables, what I'll call robot I's strategy, but also the other robot strategies. So all the other robots I'll just denote as minus I, right? It's just a cute notational trick. This is standard in game theory. And what I'm particularly interested in is a very specialized kind of game theoretic problem, which is called a generalized Nash style game. Generalized means there are constraints involved. So there's coupled constraints. And this is really crucial in robotics, right? Where one of the most common forms of coupling among robot trajectories is collision avoidance, which is a constraint. And so this is out of the domain of regular game theory, and it's a specialized subject. It's called generalized Nash games. So I am trying to both optimize my objective and satisfy my constraints, but I'm subject to all these other robots that are doing their own thing. And so what does it mean to have a solution? Everybody's got their own objectives. We're not trying to minimize the sum. Everybody's got their own objectives. So a solution, what I'm talking about is in the sense of Nash. So it's called a generalized Nash equilibrium. And it's a kind of equilibrium in the following sense. So, given everybody else is doing what they do, we'll call that theta star minus I. I have to be doing the optimal thing. That's theta I star. So that means I am optimizing my own local objective and my own constraints, and I'm obeying my constraints, subject to the fact that everybody else is doing what they're doing. And now everybody has to be in that state. We all have to be mutually optimizing our own local objectives. And that's called a Nash equilibrium. So you could think of this as no robot can unilaterally improve its objective. If everybody keeps doing what they're doing, if I do anything else, I'll be worse off. That's a Nash equilibrium, but in this case, it's specified with constraints. So in generalized Nash problems, oftentimes you have a manifold or an equilibrium, a manifold of equilibria, excuse me. So there's not a single equilibrium. Oftentimes you have just many choices of equilibria. So I'm really running short on time. So I'm going to just give you a high level idea of how we solve this problem. So we're using a solution technique that's well known in game theory. It's called iterative best response. So you have a drone race. I'm going to talk about the green drone as the ego drone. That's the one we're controlling. That's the kind of, we're putting ourselves in the seat of that drone. So how does that drone solve for its trajectory? It's trying to find a Nash equilibrium in the joint space of trajectories between itself and the gray drone. So it starts with its own optimal trajectory, and then it optimizes for the gray drone just internally. It's the green drone is doing all the computation. So it says, what would the gray drone do if I did this? Oh, here's what it would do. And then the green drone re-optimizes. This is called the best response. So it's finding the best response to the gray drone. And then the green drone again finds what would the gray drone do now? And they keep doing this until they hit a fixed point. And the fixed point is a Nash equilibrium. If you hit a fixed point, this is provably a Nash equilibrium. So that's great. The problem is you don't always hit a fixed point. Sometimes you dither, sometimes you do funny things. In practice, when you have constraints, this doesn't work at all. So for generalized Nash equilibrium problems, it doesn't work. And here's why. The first player in this iteration has a massive advantage. If the green guy plans with his objective to minimize his objective, and then the gray drone plans and he has to obey the constraints. So he has to plan fully around the green drone to obey those constraints. And now the green drone has no reason to move. He's already satisfied the constraints because the gray drone did it for him. And so now the green drone has a very unrealistic advantage, right? Okay, so how do we fix this problem? We propose something called sensitivity enhanced IBR. There's some details here. I don't have a chance to go through the details, unfortunately, due to time constraints, as you can see. But let me just sketch what's going on. So I'm robot I, and I reason about the fact that robot J has to satisfy constraints in the future. And I expand the optimal cost of robot J around its optimal decision variables, incorporating those constraints. And so that involves taking a gradient of the collision avoidance constraint, a Jacobian of the collision avoidance constraint. And this tells me what is the sensitivity of his trajectory with respect to my decision variables. And then I take that sensitivity and I plug it into my own objective function with a negative sign in front. So what am I doing here? I'm saying I am going to not only optimize my own objective, but I'm going to try to hurt the other guy. This only works in a zero-sum game. So what I'm saying is I'm balancing my own objective with the negative of the other guy's objective. And this only works if hurting the other guy helps me. That means it's a zero-sum game. And so this is specifically useful for racing, right? Drone racing or car racing. These are zero-sum games. Okay, so that's the trick. We augment our objective function with this sensitivity term, which hurts the other guy. It turns out we can solve this very quickly. So 20 milliseconds per iteration online. We have to do multiple iterations. It takes like, anywhere between 2 and 10 iterations to reach a fixed point. And then we do this in a receding horizon loop. And we have a theorem, which is that the fixed point of this modified problem, the first order conditions that define a fixed point are the same as the first order conditions that describe a Nash equilibrium for the original problem. So even though we've modified the problem, the local conditions for the Nash equilibria for both problems, they turn out to be the same. So the modification actually doesn't change the characteristics of the Nash equilibrium, locally speaking. Okay, so we frame this problem specifically for drone racing. We have dynamic constraints, we have collision avoidance constraints, we have stay on the track constraints, and we have input constraints. And at the end of the day, the objective is the drone wants to open the gap between itself and its competitors as much as possible. So I want the difference between my position on the track to be as big as possible with the difference between the other drones on the track. And this is the algorithm that I'm showing here. So this is sensitivity enhanced iterative best response for drone racing. And here the green drone is the one with the green trajectory is using SEIBR, that's our algorithm. And the blue drone is using just a naive MPC, which is the state of the art actually. So it's what you would do using a nonlinear MPC algorithm to race a drone around a track. So this is joint work. We have a TRO paper that just appeared. And my collaborators are Ricardo Spica, who's a former postdoc, Eduardo Montijano, who's at University of Zaragoza, Eric Christofoulou, who just graduated with me, and Zijian Wang, who graduated a year ago. So I can refer you to that paper for more details. So I'm just about ready to wrap up here. I know I'm over time. We have, in recent work, developed a similar racing algorithm for cars, dealing with the more complex non-holonomic dynamic constraints of cars and various other improvements. This is work by Mingyu Wang, my PhD student. And we've also implemented this on a full-scale autonomous car. Again, this is Mingyu Wang's work, where you can see my two students sitting in the car, but the car is driving autonomously, and the car is racing against a simulated opponent, because we don't want to start bumping up full-scale autonomous cars and against each other and causing damage and hurting people. So this is one car real, one car simulated. We've also scaled this up to many more drones racing simultaneously. So here's 4 drones racing simultaneously in 3D. And here in the animation, you have 6 drones racing in 3D. So we've worked on actually very much improving the speed of this computation through parallel computing. Basically, we can parallelize the iterations in the sensitivity enhanced iterative best response and get a huge speed up advantage. So this was recently published in Robotics and Autonomous Systems in 2020. And this is work by Zijian Wang. And I'm going to gloss over this. This just shows that our algorithm, Game Theoretic Planner, GTP, dominates a naive MPC, nonlinear MPC algorithm. So the lower, the lower the bars are, the better. So this is which place the robots came in. So this is first place, second place, third place, fourth, fifth, sixth place, right? So GTP is dominating. And in a different starting configuration, again, GTP dominates first, second, and third place. Okay, we teamed up with collaborators at Microsoft Research, this is Ashish Kapoor's group, who developed a high fidelity drone simulator called AirSim. We ran a competition track at NeurIPS, the machine learning conference in 2019. We called it Game of Drones. I think that's kind of cute. And we produced as a side effect, a full-featured drone racing simulator environment called Drone Racing Lab. So you can download the binaries, you can install them, and you can race your own drone in this full-featured environment. You can race against benchmark algorithms. And you can see the graphics are beautiful, and you can also work on the perception side. So there are various facilities through the API to extract various simulated sensors so that you can develop perception algorithms, and also to command the drone through various high and low level control input commands to navigate the drone through the course. This is, by the way, a real building in Microsoft Research in Seattle, Washington, that you're racing through. It's pretty cool. Okay, so as I said, this sensitivity enhanced iterative best response is only for zero-sum games. Our recent work, RSS 2020, by my student Simone Leclerc and a collaborator Zach Manchester from CMU, gets around this. So it's a completely different method. It works on solving for the fixed point equations directly using the Augmented Lagrangian approach, and it does not require a zero-sum game. And we've looked at this specifically for autonomous driving. So this solves the frozen robot problem for freeway merging. Autonomous driving currently, autonomous cars, they cannot effectively merge on the freeway. This is one of the core problems outstanding in autonomous driving, is that autonomous drivers currently use an NMPC, nonlinear MPC approach, and they cannot reason about what the human-driven cars will do in the future. They have to make simple static assumptions about what those cars will do, whereas our game theoretic method reasons about how those cars will yield for us, as you can see in this figure. And we reason about the fact that they will make way, and so we can unfreeze the robot and let them merge onto the freeway in a very humanistic, realistic way. So I'm going to go ahead and stop there. Thank you for your patience. I know I went a bit over time. I talked about distributed optimization for collaborating robots and game theoretic planning for competing robots. And I should acknowledge all of the wonderful students and collaborators and postdocs who are the true minds behind this work. And I should gratefully thank my various funding sources for allowing us to do this work. And of course, thank you to you all for your kind attention. And I'm happy to take questions.
Thanks a lot, Mac. I'll clap on behalf of everyone.
Thanks.
So audience, if you have questions, you can raise your hand and I can unmute you. There's a couple of questions here, so I'll just read that out in the interim. John Lathrop asks, how is the ability of drones to hurt their opponent's objective function changed if the opponent drone has a different or only partially known objective than the self drone. So looking at the
That's
asymmetry, I
amazing.
guess, in the objective.
That is the core problem that's outstanding, is two things. How do you influence your opponents, say, when their objectives are not the negative of your own objective? I think that was part one of the question. And part two was, what do you do if you don't know their objective functions? So we are working on both of these things. So the first point of that question I addressed, but way too quickly, and I apologize for that, in the very last segment of the talk. So in our latest work, we are not doing sensitivity enhanced iterative best response. We've developed an entirely new solution technique. And what it does is it takes the coupled game, right, the generalized Nash equilibrium game, directly writes down what the first order conditions are for a Nash equilibrium for that game, and then solves those first order conditions. Those are algebraic now. They're like KKT conditions in an optimization problem. So then we solve those algebraic equations with a Gauss-Newton method. So we're doing root finding. We're not doing optimization, we're doing root finding on the KKT conditions for the Nash equilibrium directly. And this allows us to reason about how I can influence the other guy's cost, even though it's not the negative of my cost. And it just happens through this algebraic coupling of the KKT conditions. And our solver is very fast. It actually can solve for up to like 4 cars over several seconds horizon. It can solve in maybe half a second the coupled trajectories of all those 4 cars. For 2 cars, it can solve for the full trajectories for the 2 cars in something like 30 milliseconds or 40 milliseconds. So it's fast enough to do this in a receding horizon loop online.
Awesome.
And then the last, I'm sorry to be long-winded, the last part of that question is, what if you don't know the objective function of the other cars? And we're working on this. So we basically have an online inverse optimal control problem that uses our solver, game theoretic solver, internally. And this is what I'm showing here. So the red car doesn't know that the blue car is trying to avoid collisions with those yellow obstacles. Those yellow obstacles are basically reflected in the objective function of the blue car. The red car is us, and he is taking observations of the blue car, and through inverse optimal control, a particular brand that we've developed, he is online learning the objective function of the blue car, while at the same time planning a game theoretic trajectory, a Nash equilibrium trajectory with respect to that blue car. So we have a forthcoming paper on this.
Awesome.
Okay.
Dinesh has a question. Dinesh, go ahead.
Pratap, can you hear me?
Yes.
Good. Mac, nice talk, and you covered a lot of stuff. So
yeah.
You showed quite a few. In fact, the very last time, you showed this simulation in Carla with, if I remember correctly, 50 autonomous cars, 50 drivers, and you're showing this, and you talk at the end, the freeway entrance problem with the MPC issues.
Yes.
So one challenge that comes up in autonomous driving, is that when you autonomous cars are more predictable, but human drivers are very unpredictable. You don't know the person next to you driving is on a cell phone or losing off. So the top plot and Carla, the results, just to look at Carla simulator, it's like a very simple.
Yes.
Life is too good if everybody's driving so nicely in a nice.
Absolutely.
So how do you take into account this unpredictability of human behavior? Can you model that with some control theoretic or probabilistic distribution in the formulation?
It's again a wonderful question. This is I'm not surprised that you guys are identifying the most important issues that need to be worked out after beyond what I spoke about. By the way, Dinesh, I don't think we've met in person, but I really enjoy your work. Specifically your reciprocal velocity obstacle and velocity obstacle work with your. So yeah, we are working on this. I don't have a backup slide, unfortunately, but we are working on this through the lens of risk sensitive control. So within optimal control, you're probably aware, or maybe not, I don't know, but many of you are probably aware that there's a brand of optimal control which uses what's called the entropic risk measure. There's an amazing fact that you have the standard LQR solution for linear Gaussian vehicles or linear Gaussian systems. You have a risk sensitive version of that exponentiates the LQR objective function that incorporates, it actually penalizes variance in the solution. That's why it's risk sensitive. You're trying to find a solution that has a low average cost and also low variance on that cost. And this is classical work, by the way. It goes back to the 80s and even earlier, back to the 70s. So in the linear Gaussian case, there is a Riccati equation solution for this risk-sensitive optimal control. So in work that we've done, this is actually just published in IROS this year, 2020. We have formulated this into a game, and then extended it to the nonlinear, non-Gaussian case. So we've basically have an algorithm called iterative linear exponential quadratic games, where we successively linearize all the agents. For all those agents, we solve a coupled risk-sensitive game, just like a LQ game. There's a closed form Riccati solution for that. There's also a closed form exponential risk version of that game. And then we take that solution and relinearize about that solution, and we iterate until convergence. So this gives you risk-sensitive behavior. So the one robot is observing an unpredictable robot, and it will take actions to avoid the kind of risk envelope of that unpredictable robot. I'm not saying it's the only way to do it, but this is something we're working on. So it's a great question, Dinesh. Thanks.
I'll follow. There's some idea. I'll follow with email with you if you have time.
Okay, sure. Yeah, I'm happy to send you the paper.
Awesome. There's a question from Michael and then John. So Michael has a question. Michael Oti.
Hey,
he's asking.
Michael, how are you?
Well, I guess he's not plugged in his mic, but he says he's
okay.
good. So his question is in Bertsekas and Tsitsikli's work, if he remembers correctly, the convergence requires the following property. If node I communicates with another node J once, then it must continue to communicate every once in a while forever.
Yeah.
Since in your case, the communication is changing as the robot moves, do you have another trick to guarantee convergence?
Yeah.
If not, what sort of convergence guarantees exist?
Yeah, it's a great question. So essentially, this is solved in the following way. So our optimization algorithms are taking place within successive time steps. So you have big time steps and little time steps. So for the sake of this target tracking problem, all the robots take a measurement. Okay, for the sake of argument, we'll say it's synchronous. All the robots take a measurement, and then they perform their distributed optimization. And in practice, this is very fast. This converges in sub-seconds, maybe half a second, maybe a third of a second. And so we are assuming that through the course of this optimization, the graph topology doesn't change, or if it does, it has this recurrent property that's required for convergence. I mean, for autonomous cars, things that move on the scale of autonomous cars, that's fair. One could argue that that's fair. I'd say it's an interesting thing to look at in the future. So then, as long as this holds through the interval between two measurements, that's all we need in this short time scale, sort of half a second time scale. And then when we go to the next set of measurements, the population of robots, the graph topology can be completely different because we're restarting the optimization.
Awesome.
But it's a good question.
So I'll let John ask. So John, go ahead.
Hi, this is John Barnes.
Good to see you. I think we've met a long time ago, but it's a pleasure to hear from you.
Yeah, very nice talk. I have several comments to make, okay. First of all, regarding risk-sensitive control, I don't know if you know that, but we have completely solved the nonlinear, finite state, hybrid automata, set-valued, risk-sensitive control back in the 80s with a bunch of students. And the importance of these results is that we know the complete structure of the solution. It involves two Hamilton-Jacobi-Bellman equations, one going forward in time that you have to solve real time that computes the information state, and one that is offline that computes the control as a memoryless function of the information state. Mm-hmm. The unfortunate thing is that in all these categories of systems, you cannot solve these two equations. And but knowing the structure, it gives you a lot of ideas about how to propose approximations. And we currently, with 3 students, we are extending this to network systems because that work, which extended way beyond the results of Doyle, Kagonecker, and Francis, etc., or from linear Gaussian systems, right? So you should look at that and try to see if you can come up with some ideas for the network problem. Now, and I have many questions, but we can talk offline. But one important question I want to ask you is this. In many of these problems, including the problem that you mentioned, the merging, as Diane mentioned, okay, we try to go away from assuming functional forms of the costs because you do not know them. And remarkably, we have shown that just for measurements, even you can actually do this problem. As long as you're willing to combine both calculus and formal methods, you can actually do that. The most important parameter, or the most important unknown, as Diane already mentioned, is the fact of trying to estimate quickly the cooperativeness or non-cooperativeness of the other driver. I mean, even if you had everything autonomous and you measure velocity and position, the problem is very doable, very fast, just by measurements, without assuming any function of the costs. And even in the case where you have the humans, because for humans, you cannot use causality, you know all that. Humans are not causal systems. You do not know what the guy is going to do, if he's going to like you or not like you, if he's going to let you pass or whatever. So this is very active research, actually, in many places to try to very quickly and online estimate the behavior, both in terms of the so-called car passing problem that we have studied both here in KTH with Kalle, and also in the merging problem that you described. Okay. So that's very, very nice stuff. If I had a suggestion, try to see what can you do if you get rid of the assumptions on the functional form. Because with Anoop Menon and others, following the work of Mandler and others, we were able to show that with measured utility, you can get very simple controls as long as you understand the implications of the actions of one player to the other. All right. That's following up the old work of Peyton Young and others. Okay. I mean, unbelievably simple controls. Okay, because you don't have to estimate the function, you don't have to solve the inverse problem control, and so on and so forth. All right. So that's my remarks.
Okay. Yeah.
Thank you very much for a very interesting talk.
Thanks. I'll look at the pointers that you mentioned. Yeah, absolutely. I mean, I'm aware of these kinds of Pontryagin principle style 2-point boundary value problem solutions that sort of, generalize the optimal control solution to the game theoretic problem. So what I frankly am not aware of the work that you mentioned that only requires where you don't have to have complete knowledge of the other car's objective. You very simply through data reconstruct some.
There are people that worked on that. It was Peyton Young, Marden, myself. Okay, there's been at least 100 papers on these topics where you try to. It started with a paper by Peyton Young and Marden, and then we extended it with Anoop Menon, who's actually Waymo. Is in your area.
Okay.
So and we saw this result again. So yeah.
So one of the key things that we're interested. I mean, you mentioned these algorithms are fast, but so I don't know exactly how fast. But one of the key things that we require.
No. They are fast if the topology has properties.
I see.
I mean, that's why I keep asking you all these questions at the beginning. And I hope you get copies. Is because what we have shown is that the topology of the communication graph is essential in proving fast convergence of these distributed algorithms. All of the above you mentioned, okay? Because, and we run across this special group of graphs that they are called expanded graphs, that they are extensions of small world graphs. And for instance, we use this with Anoop Menon to solve the so-called platoon stability problem in control for 40 years, right? We are able to show that if you allow communications beyond nearest neighbor, which in wireless communications is the natural thing, right?
Right.
Then the platoon can be stable, right? There's no problem, okay? The problem is artificial, okay? So, This is my big problem here is that most of the community tries to model network control systems with one graph. And then you ask people, what is the link?
Yeah.
They cannot give you an answer. We use actually 3 graphs. We use collaboration graph, which says who collaborates with whom when.
Yeah.
We use communication graph, who communicates with whom when. And we even use an information graph occasionally about where you keep your models and so on and so forth, etc. And it's
Makes
fascinating to try to understand the interplay between these graphs
sense.
as far as convergence. Yeah, right.
Yeah, I appreciate it. Absolutely. I really, I hear your comment. It makes a lot of sense.
I'll send you some links and some emails.
That would be great. If you could, that would be great. I would like to point out a few things. So firstly, in all the game theoretic work that I talked about, there's no communication graph because the ego vehicle is doing all the computation to sort of predict what the other players will do. Yes. And that's the only sensible way to do this, right? If you want a robot to cooperate with human drivers, the human driver.
But then there's an important point here that I put in another question is, okay, important in our work was trying to discriminate between what we call direct communications, where I send a signal, versus indirect communications, where I use the sensing and your motion to communicate. That, like you do in team sports. Okay?
Right, yes.
And that is inspired by biology, and you can get tremendous mileage out of this very simple idea. When you play soccer, you don't call each other to the phone, right?
Yeah,
you just move a certain way, and that means something, right?
That's a signal. Yeah. We've written some papers on that idea as well.
That's right. Yeah.
So I do want to point out one other thing that is probably an important distinguishing element between. It looks like my PowerPoint just froze. Can you all still hear me?
Yeah, okay.
We can hear you.
Okay.
Yeah.
Okay, so I'll just talk through it then. I was going to try and change slides, but this last solution method that I described, we're actually trying to solve the system of algebraic equations, which describe the first order conditions for Nash equilibrium. So this is exactly the same as Pontryagin's principle, but it's in discrete time. So everything I'm talking about here is in discrete time. So this is exactly sort of minimizing the Hamiltonian, but in discrete time. In fact, you could decompose the first order conditions to look like sort of Riccati equations or first order, 2-point boundary value problems where you have a path that goes forward and a path that goes backwards. It's the discrete time analog to that. What's, I think, special about what we're doing is one of the key things we worry about is collision avoidance. So I don't know the work that you're talking about in detail, John, but my guess is it probably does not directly deal with constraints.
It does. At least in our work, everything we have is the constraints. Let me just make one last remark because everybody needs to know that, okay? So what we showed when we solved the risk-sensitive control problem is the following remarkable coincidence of 3 problems that they were initially completely unrelated. In other words, you formulate the robust output feedback control problem as a game problem, which goes back to the Russians in the 50s. Then you saw by randomizing this problem that you can turn it into a stochastic control problem, which is partially observed. And out of this, by the Laplace approximation, the so-called entropy control, the exponential of an integral, comes automatically out of the math.
Yeah.
You don't have to assume it or anything. It comes out of this. And it is actually related to maximum entropy. So all of these mathematics have been worked out.
Yeah.
And then, so you have the equivalence of the stochastic control problem, you have the equivalence of the game problem, and the risk-sensitive control. And that allows you to prove a lot of things in these very general nonlinear systems, hybrid automata, and even set-valid systems, okay?
Yeah.
But
you
know the structure, but the computation is impossible. So approximations is in order, and we're working on these things, right?
But you have to optimize the risk sensitivity parameter, right? You have to hit what's called neurotic breakdown for this to actually represent the game, right?
What people have done even here in Maryland and other places is we now have moved into more general risk problems because right, thanks to the Nobel Prize winning of Tversky, and Kernighan, right, that humans do not decide on the basis of maximizing expected utility, okay?
Yeah.
They also take into account risk.
Right.
And this given, again, a rebirth on importance of risk-sensitive control, right? It's called prospect theory. Prospect theory with the Nobel Prize winners was very formal. They introduced these S-curves. So people here like Michael Fu and Steve Marcus and myself are working to try and to bring different notions of risk into these
Yeah.
problems, right? And do the
Yeah,
trade-off between risk and performance, right? Yeah.
That's really exciting. Yeah. So this paper that I hinted at, which I didn't have slides on here, that's appearing in IROS this year, is the game version of entropic risk optimal control. So I'm happy to send that to you. And then also, you mentioned prospect theory and different notions of equilibria that aren't just the standard Nash equilibrium. So there's this like quantile response equilibrium idea, and I'm working with a postdoc and a student to develop actually an optimal control algorithm for cooperating groups of agents to find this quantile response equilibrium, and then also an inverse optimal control algorithm that does the same thing but without the robots knowing what one another's objective functions are. So it sounds like we're working on a lot of similar problems. So I'd be happy to read up on what you're working on.
I mean, this is a fascinating conversation, and I hate to break it up.
Yeah, maybe we should take it up.
Yeah, but this, I think, I mean, I would be interested in hearing more about this conversation. So hopefully you can continue this offline. But on behalf of everyone, Mac, I would like to thank you for taking time out and presenting very interesting research. As you can see, there's a lot of excitement about the kinds of things that you're doing over here. And hopefully one day you'll visit us in person. And,
I would love to.
Visit the university. Thanks
for the amazing questions and the conversation. I mean, this is very enriching. It's great to hear all the insights and the pointers to the literature.
Awesome. All right, so it looks like there's lots of follow-up conversations to be had. Thank you, everyone, and thank you, Mac.
Thank you.